Guess what, everyone? Today we're going to start a new unit. That's right, we're going to continue our study of algebra by beginning a unit on systems and matrices. Now, there's a good chance that both those words you have some exposure to, but I would bet that there's definitely concepts that we need to review. I'm sure there'll be some new concepts, and like this whole year, we definitely will have some ideas that also challenge you to some new lengths. So let's get started. And probably a great place to start is to just think about what do we mean when we're talking about a system. And so today we're going to solve some basic systems. And remember that a system is really when you have a couple equations that are solved simultaneously. That's really a fancy way to say find the intersection point of your lines. And I imagine that the first time that you solved a system, that's exactly what the teacher did. And I just want to take a quick moment to review that technically we're looking here at a line y equals negative 2x plus 4 and the line 1/2 x minus 1. Now, if we were going to use a graphing method on this, we could very simply think about how to draw a line that has a y-intercept of 4, but that's not too hard to do, and a slope of negative 2. I think that we have a pretty good sketch of negative 2x plus 4. And then I could think about drawing a line that has a y-intercept of negative 1 and a slope of 1/2. Now, obviously, my answer is only as good as the accuracy of my graph. If I was able to graph this on some nice paper, or maybe using Desmos, it would be a lot easier to see that intersection point, which is at, it looks like, 2, 0. Now, remember, the intersection point of two lines is also going to solve both of those equations. And of course, it's going to solve those two equations, meaning as a solution. So I should be able to plug a 0 in for y into my first equation. And I should be able to plug a 2 in for x. And we find out that if we do that, we end up with a true working point. And if I plug in to the second equation, again, if I plug a 0 in for y and I plug a 2 in for x, well, I find out that we get the same outcome. We get a nice true working solution. And remember, that's always the case. Even if we don't go back and plug them in, it's always the case that a point that is a solution has to work in both equations. What if I didn't want to graph my system? What if I wanted to maybe solve my system using more of an algebra method, like a substitution method? Well, remember that if you have the ability to take one of the equations and substitute it into the other equation, then you're using a substitution method. So try it with me. If you substitute negative 2x plus 4 in for y, then you get negative 2x plus 4 equals 1/2 x minus 1. Now, I don't know if you're excited about solving this equation, but I do know that it's solvable. What we want to do is kind of gather up the x's, that is, kind of move the x's to one side of the equation and move the numbers to the other side of the equation. I feel like I could subtract 4 from both sides. That's definitely legit. And if I want, I could subtract 1/2 x from both sides. It is a fraction. It's kind of a pain, but I can do it, right? Now, if I subtract 4 from both sides, then we end up with negative 5. If I subtract 1/2 x from both sides, then I got to do a little thinking about fractions, and I end up with, I guess it's negative 2.5 x. Now, if negative 2.5 x equals negative 5, then I can just divide both sides by negative 2.5, and I think I end up with, well, with the same x value. Of course, x equals 2. Remember, that's what we found in the other problem. Now, if x equals 2, technically I have to plug that back in. Let's not use black. Technically, I have to plug that back in for x, and I could plug that back into either one of these equations. I kind of feel like it'd be a little easier to plug it into the first equation. And if you do that, you're going to get your y value, which, remember, we actually already found comes out to be 0. But the point is that I can still find a point. That is, I can find an x and a y to be 2, 0 using a substitution method. Do you remember there's another method? We have graphing, we have substitution. That's right, we have what's known as elimination. Now, this is a new system, so if you haven't taken any notes yet, you might want to take some notes with me, or you can keep watching, but either way, please know that this is a new system, and we're going to solve this using an elimination method. Now, remember, elimination works by basically arguing that you can add the equations together, but before you add the equations together, it's nice to have opposites, because you want to make something eliminate. So what do you think? If you multiply the top equation by what? By 2, then you'll be able to make the y's be opposites. And so we get a nice little 4x, we get a nice little minus 4y, and we get 18. Don't forget to get 18. Sometimes kids will forget the constant, which is not a good idea. But now I can add my new equation with my existing second equation. And I think if I'm doing this right, I'm going to end up with 12x equaling 18. And I guess as you keep solving this, you could solve for x by dividing by 12. It's not going to work out to be an integer. I was kind of double checking myself to make sure that everything was fine. But that's all right. You're allowed to get a little decimal or fraction. And 18 divided by 12 is 1.5. Now, just like we did in the other problem, you definitely need to find the second answer, and that means taking your x and plugging it back in. You can plug it back in for any x that you want. I'm just choosing to plug it back into the second equation just so you guys can see that I'll put 1.5 back in there and do what I got to do to solve that for y. I'm pretty sure if you solve that for y carefully, you're going to end up with 12 and 4y equaling 0. So a little bit of algebra would tell you that y equals -3. The important thing here is that you realize that once again we found a point. That means we want to give the x and the y. Notice that I actually wrote it as an ordered pair, which makes it super duper. So substitution, elimination, and the graphing method. Now you can use any of those methods that you want to tackle any problem that you see, like this system. We have y equaling 4x plus 1 and -8x plus 2y equaling -6. You feel like you want to kind of try this on your own? I encourage you to. You can pause the video. Are you thinking about a substitution method? Okay, now remember, when you use a substitution method, that entire quantity of 4x plus 1, that entire quantity is getting plugged in for y. That means that we definitely want to use grouping symbols. Make sure you use grouping symbols because that 2, that's right, that 2 is going to distribute. It's going to multiply to both. What do you think? Are you working the problem through? -8x, +8x, and plus 2 equals -6. Well, unless I made a mistake, which we didn't, looks like those x's are going to cancel out. Looks like we're just going to end up with 2 equals -6. Well, does 2 equal -6? Not last time that I checked. And I believe that we have what's known as a false statement, which can be interpreted as no solution. Now, if you think about it, the reason this problem is no solution is because we have 2 special lines. If you think about the 2 lines that you have in this problem, you quickly deduce that your 2 lines have the same slope. Here's my first line, the first equation, that is. And I think if we graph this second line carefully, what are we going to have here? We're going to have a line that's down here. But either way, where do those 2 lines intersect? Well, you're right, they don't. And so we don't have a solution to this system. But notice that's because we got this false result when we did the substitution method. Okay, well, that didn't work, but let's take a look at this next system. What we have here is 3x minus 2y equals 5, and then 4y minus 6x equals negative 10. Same thing. I encourage you to think about this a little more on your own. And once you're done copying it down, do you notice something? Yeah, do you notice that that second equation seems like it's sort of out of order? Okay, you got to look carefully, but the truth is I need to change the order of my x and y. I need to make sure that things are consistent, that they kind of look the same in both equations. So I'll tell you what, we're going to take this system here off to the side, and even though I didn't change anything in the first equation, I definitely want to change my organization of my second equation. I want the negative 6x to come first. I want the 4y to come second. So I end up with negative 6x plus 4y now equaling negative 10. Okay, well, it's still the same system, so we want to solve it. Are you feeling like an elimination method? Are you feeling like you could multiply the top equation by 2? Okay, yeah, that's going to give you some opposite variables. Looks like now we have the opposite x's. Looks like I now have the opposite of the y's. And, oh, geez, it looks like I actually have the opposite of the constants also. Okay, now I'm adding the gold and blue equation because those two equations have kind of been changed so that I have opposites. But yeah, when I add them together, it seems like I end up with something, well, once again, that's kind of strange. Now, it definitely is strange, but actually it's quite the opposite of the problem we just did before, because if you think about it, 0 does equal 0. We end up with a true statement. Now, when we end up with a true statement, that doesn't mean no solution. That actually means that I have an infinite amount of solutions. Now, if I have an infinite amount of solutions, it turns out that my two equations that I originally had over here are actually the same two lines. They're the same two lines because they're basically intersecting everywhere. If I was going to graph these two lines, I probably would end up with a graph that I suppose looked, if we think about this a little bit, yeah, I'm going to end up with a line that kind of looks like this. And if you believe me here, the second line looks like that. And basically they're the same two lines. And that's because and of course now they intersect everywhere, which is why we have an infinite amount of solutions. I'll tell you, the last two problems we did were kind of special, and they bring up what's known as a classification system for systems. Now, the way that we classify systems is by using a couple words. They might not be words that you use with your friends, but they will be some words we want to use in math class. Now, we can either have a consistent system or an inconsistent system. And let's find out here. A consistent system is one that has a solution. Okay, now the first couple problems that we did had solutions. Remember, they were just a nice little intersection point. But the last problem that we did, it had an infinite amount of solutions. Okay, so we have like two subcategories. Now, the first subcategory is the idea of being independent. Independent means you have exactly one solution. Okay, that would be like the first problems that we did. Dependent means that you have an infinite amount of solutions. Okay, like the last problem that we did. And if you have an infinite amount of solutions, as I showed you in the previous problem, that means that we have the exact same two equations. So a system can be consistent and independent, or a system can be consistent and independent. And then we have a system that's inconsistent. Can you take a guess what that one would be? That's right, it's going to have no solution. It's going to have no solution. Now remember, if a system has no solution, that means that your lines are parallel. And when lines are parallel, they don't intersect. Usually a good exercise is to go back to the problems that we did and just give these classifications for each one of them, just so you understand exactly what I'm talking about. So I'm going to flip back And do you remember the first one that we did? It basically had a nice intersection point, and that means that the system was consistent and independent. It was consistent and independent. So notice how I use both of those words, because again, I have a solution and I have one solution, which is normally the way that it works. Okay, so here's the same system. It's still consistent and independent. How about this system? Okay, it was a new system, but once again, it had a nice point. It had one solution. So again, it is consistent and independent. We use both of those words so that we can be as exact as possible. Now, we got to this system where we clearly have parallel lines where we had no solution. Basically, another way to say no solution is inconsistent. Inconsistent is the same thing as having no solution. And then the last one that I did, you got to be a little bit careful here, because sometimes when everything cancels out and you end up with zeros like we had right here, kids want to say no solution. But remember, it was actually the opposite. It was an infinite amount of solutions because the statement came out true. Now, that means that this system is consistent but dependent. It's consistent but dependent. It's got a solution. In fact, it's got an infinite amount of solutions, and that's what makes it dependent. Okay, now for our final problem today, I want to make sure that we can handle a system that maybe initially looks crazy, but with a little bit of magic, we can say, okay, yeah, that system's not that bad. And then we're going to encourage you guys to solve some systems as a little review through your homework helper. Okay, so what do we have here? We've got a 0, 2x minus 0, 5y equals a negative 0.38, or 0.38. And then we have a 0.03x plus a 0.04y, and it equals 1.04. Okay, now I'll say here that although this system looks like it's a bunch of decimals, it's really just decimals in disguise. Okay, because it's a great opportunity to remember that if you move the decimal, and of course, if you move the decimal 2 places, you're not going to have decimals anymore. So multiplying by 100 is a perfect way to move the decimal 2 places. And I can multiply both equations by 100 and basically end up with kind of a new and improved version of each one of these, which just ends up being 2x minus 5y equals negative 38. That's a heck of a lot better. And what else am I going to get here? 3x plus 4y equals 104. So now what? Well, I hope you're thinking about using the elimination method. That's going to be a lot easier here because I've got both these equations kind of written in standard form. So let's get some opposites. Now, as you look this over, nothing is an opposite as it stands, but at least the y right here is a negative versus a positive. And so what I'm going to do is I'm going to focus on changing the y's to both be 20s. Now, the number 20 is actually what we call the least common multiple. But basically, it's the smallest number that I can turn both of these numbers into. So are you with me here? We're going to get 20s. That means you're going to multiply the top equation by 4. That means you're going to multiply the bottom equation by 5. And I just want to make sure you guys remember that you're allowed to do this. You're allowed to multiply both equations by a number. Of course, you're going to end up with some new numbers. Make sure everything gets multiplied by 4. Oops. So that means an 8x. Now here's our minus 20. That's what we were looking for. And 38, negative 38 times 4, that's 152. I had to check that on a calculator. So yeah, multiply everything by 5, 15, 20, and 520. Yeah, 520. Okay, I feel like I've changed the system now a couple times, but that's the idea. You can change it as much as you need to, as long as you're multiplying every number. Finally, when I add these equations together and get 23x, that means, or now the y's will cancel out, and I'll be left with 368 over here as my constants. Okay, and then you're on your way to solving for x. Okay, divide both sides by 23. It is nice that it works out to be an integer. It doesn't have to be an integer, although a lot of answers are. Now, once you get x equaling 16, what do you want to do? I hope you want to plug that back in. Where do you want to plug it back in? I don't even want to go back to these decimals, so I'm not going to plug in there. But it probably would be easier to plug 16 into one of these smaller equations, like maybe this equation here that has smaller numbers like 3x, 4y, and 104. That's what I'm going to argue anyway. I'm going to plug into this one. And when I plug in, I'm going to end up getting 3 times 16. Let's keep with the colors here. So we get 3. We're going to substitute in 16. What else do we have? Plus 4y. And that was equal to, if I'm not mistaken, 104. Okay, so I think we're going to end up here with 48 and a 4y. And if you keep trusting the math here, 4y, when I subtract 48, what are we going to get? That 54, 56. So we end up with 56. And then I'm pretty sure when you divide 56 by 4, it works out nicely to be, I hope, to be 14. Right, it ends up being 14. Okay, so y equals 14. Whoops, I'm dividing by 4, right? So if you're dividing by 4, that's why y equals 14. All right, so we end up with a nice point here, which, remember, we want to write our answer as a point. So we get 16 and 14. I can write that a little better. All right, but just kind of remember where this problem started. We multiplied everything by 100. It was definitely legal. And then I multiplied both equations by different numbers. The 4 and the 5 gave us the 20s. And from there, we used the elimination method and got our x and y.